Hi everyone, yeah, I'm Loic. I'm not going to talk so much about what I am working on today, but I'd like to talk about the problem that I'm interested in. So I'm going to take a step back and look at some different work in the literature that I think is interesting and quite cool, and discuss what I think is interesting and challenging about the application of shape representation learning. So to be clear, I'm going to focus mostly on deep learning methods and what they have to bring to the problem. So whether it is neural networks or deep probabilistic models, and especially generative models, because generative models will let us have an insight into what the model has learned. So I'm going to skip most of the traditional shape analysis methods, but it's good to keep in mind that they exist, because there are many such methods, and they are honestly quite good in general and very powerful. Even the simplest one, like active shape models. Of course, they still have a few limitations. For instance, active shape models, essentially it's a landmark representation of shapes, and on top of it, a PCA model. So it's essentially a linear model. So it's not really meant to cope with non-linear variations, such as large variations in geometry that you could observe or encounter in pathological populations. So maybe with deep learning we can overcome some of these defects. Maybe the very first question that we could ask is, can we just, very naively, could we just forget everything about shape analysis and just train a huge neural network that takes an input data set and solves the task? So we can actually look at the ShapeNets paper where it gives a few elements of answering to this question. So it's a paper in computer vision, because most of in the past 5 years, much work has been done in the computer vision and computer graphics communities. So it's interesting to look at this community. So, yeah, sure. Yeah. Tell me if you still can't hear me. Is it better if I do that, or still bad?
You can also speak into this one.
Yeah.
This one.
People start to get. Is there rain coming in on this side?
Can you hear me if I speak now? Yeah, good. So yeah, the setting for ShapeNets is the authors have come up with a large data set of computer-aided models. And it's really a huge data set with many, many different types of objects. I don't know, airplanes, chairs, windows, cars. You've all seen that kind of data set. And the idea here is, can we just take that data set and learn a generative model of these shapes? So the way they represent shapes here is as binary volumes, so they are rasterized on binary volumes. So if you have a binary voxel, 1 it's inside, 0 it's outside. And the idea is that by taking this representation, the advantage is that you can leverage all the existing literature on image-based neural networks. You don't have to do to get out of your way to work on shapes. And what they propose to do here is to train a convolutional deep belief network. So the idea is, if you look at these layers, so here, let's start from here. You have a latent code that you project onto a 3D small volume, and then you have successive convolutional layers which upsample this very small volume into a fully rasterized binary shape. It's still a very small resolution, 30 by 30 by 30. It's trained by contrastive divergence. I skip the details. What's nice about this architecture is that it makes it relatively easy to sample new examples once you've trained the model. So condition on a given layer, it's relatively easy to sample from the layer below or above. So you can generate new shapes by deep sampling. And that's what they show in the paper. Here on the left side, you have different generated samples for different classes. And I'll leave the more quantitative details for the paper itself. the take-home, it's quite exploratory really, but the take-home message is they can, with ShapeNets, they can generate new samples, they can train this generative model, they perform as good as a state-of-the-art on 3D shape classification and 3D shape retrieval. And they can also do fancy things such as reconstruct 3D models from 2.5D depth images. That's what I show here on the right. So maybe what this paper really showed is that it's actually possible to train these generative models on a very large heterogeneous datasets. I think it's what was really cool at the time, and get reasonably plausible samples. You can see maybe some topological defects, things like that, but it's not too bad either. Maybe what could be improved about this model is that sampling is not really trivial, because it's a deep Boltzmann machine, so you have to do these back and forth passes to get good samples, and usually it has to be initialized reasonably well, let's say from a training dataset, and then you do back and forth passes to obtain a different sample. So this aspect actually, it was improved in subsequent work, where instead of using a deep belief network, they proposed to use a 3D GAN. So forget about the deep belief network architecture. Now what they are doing is they have this latent space code again, Z, which again by a set of convolution is turned into a fully fledged image, and the discriminator in their framework would learn to discriminate artificial samples generated by the generator from real samples in the dataset. So the training is quite standard as far as it can be for GANs. And maybe, so in the paper they show a fancy application again, which is to reconstruct 3D models from 2D images. So you're given a 2D image, and you slightly modify this GAN architecture with a variational autoencoder jointly. They share the decoder and generator parts are shared. And with that trick you can reconstruct a 3D model given a 2D image, which is quite cool. But maybe what's more interesting here for our purpose is to look into the properties of this latent code. And some interesting properties is that because of this GAN framework, compared to the previous framework, samples generated will be generally more plausible because most latent codes will map to plausible shapes. So it improves the generating capacities of the framework. Another interesting thing that they show here is the type of arithmetic that you can do in the latent shape space. So you can say, okay, I'm going to take a chair, to remove the arms, and to add them back to another chair in the dataset. You can manipulate shape that way and create new reasonable models by doing this kind of arithmetic. Maybe to go back to one of the limitations of this work, as you can see in most of these shapes again, it's that you can see some structural defects that as a human really seem weird, as in you wouldn't do this kind of mistake where you have holes in the chair, right? It doesn't really make sense. Or you have missing parts. So it would be interesting as a next step to see if this kind of defect can be overcome. Again, to summarize the advantages of the challenge, maybe the main advantage to mention again is it was working on a large heterogeneous database. How long do I have? Yeah. It was working on a large heterogeneous database. Again, this framework of GAN using image-based neural network is quite sound and allows to avoid most of the difficulties from using directly meshes. On the other hand, the challenge, again, are topological defects, lack of invariances. You don't capture the natural invariance that you have in shapes. And it's missing some amount of understanding of what the shape is. If you have a chair as a human, you understand that it makes a subpart, a hierarchy of subparts, and how they are put together. But this kind of model doesn't capture this kind of hierarchies. But actually, if we look at some work, so this work here was proposed by Lee and his colleagues. It's called GRASS, stands for Generative Recursive Autoencoder for Shape Structures, and they tackle exactly this problem, which is to say, can we actually generate better samples by capturing this kind of high-level structure separately from the low-level geometry. So what they call the low-level geometry here would be the really fine-grained voxelized binary volume that you have, as opposed to the high-level structure, which would be the way in which the subparts, let's say here of the chair, are configured together. So maybe the fact that the legs of the chair are adjacent with this part here, and you have some kind of symmetries. So you can have rotational symmetries, reflectional symmetries, and so on. So they will build two different blocks to capture separately these two parts. So you have a neural network which is in charge of recursively building these hierarchies until you have a representation for the whole chair or the whole object you're interested in. And once you have this code for the structure, you use it to generate the fine-grained geometry. So the fine-grained geometry will be encoded and decoded conditioned on the high-level structure. The first step is to specify the simple rules that they use to have to build this grammar, this hierarchy. Again, the rules are simple. The parts are given. It's not learned. It's just given as it's a prerequisite. And the different types of rules under which you are. So the idea is you take two parts. Each part is represented by a code. And you're going to merge the code of these parts if they satisfy some conditions until all parts are merged and you have a code for the whole object. And the criterion to merge parts is either they are adjacent or there is some kind of symmetry that they follow. For instance, rotational symmetry, again, translational symmetry, or reflexive symmetry. Of course, you can have many different ways to merge this part together. So you could do adjacency first, symmetry afterwards. You can really combine it in many different ways, but it doesn't really matter here. There is a trick. So back to the idea. The idea is this kind of hierarchy. It's going to be encoded automatically via a recursive neural network, a recursive autoencoder. The recursive autoencoder takes two codes, generates one code. At training time, so the trick is that you learn to encode a variety of hierarchies. So you're not bound to one specific type of hierarchy. You really can cope with different possible variations around the most sensible hierarchies. And at test time, when you encode, I'm going to skip the details, but there is a greedy, sensible heuristic to decide exactly which hierarchy you're going to use to encode the full shape. And when you decode, of course, you have to know in which order you merge parts. So this is also learned via another network. You learn to predict whether you need to split via adjacency or split via symmetry. This summarizes the architecture. You can focus maybe on the left side at first, which describes the training. So again, the idea is you have these oriented bounding boxes, which are represented by 12 parameters. So let's say the height, the width, I don't know, the orientation in space. Which is encoded into an n-dimensional vector, and then recursively you're going to merge these n-dimensional vectors using either an encoder for adjacency or an encoder for symmetry, which are independent. And you have, in a similar fashion, you have a decoder for adjacency, a decoder for symmetry. Each of those building blocks is a two-layer neural network with this very simple shape presented here. And yeah, and this forms a recursive neural network. Again, the loss that is used here is a reconstruction loss. And let's say you fully encode, you fully decode, and you're looking at the discrepancy, the sum of discrepancies for each individual part. Okay. And at testing time, so again, what you would do is you have a new shape, the parts are given. You greedily find an optimal hierarchy based on the reconstruction criterion. I've skipped the details, which gives you a simple code for the whole shape, and then you can decode it following the steps that I highlighted before. Here is an example of what happens. So on the left side, you have the input structure, right side, the recovered structure, and the tree. This is a tree-like representation of this process of merging or splitting structures, which is quite This is what the authors show in the paper. It's relatively intuitive. It follows some of the things that as a human you would judge as a good hierarchy. And the other part, this one is a bit maybe faster to explain, is about geometry synthesis. So now you know how to encode the high-level structure, and you want to use that to inform the generation of the low-level geometry. And by doing this context-aware generation, you make sure that you can't really have that many topological defects compared to a flat generator. So the way they proceed is, for each part, they use this tree-based hierarchy to get a contextual feature, and then they want to map this feature vector. They want to learn to map this feature vector to a volumetric rasterization of the object. Okay, I'm trying to go fast. And the way they proceed is by introducing a low-dimensional code in the meantime, and they train a VAE GAN architecture to do that. Again, the training details are in the paper, but it's relatively standard for this kind of architecture. And here you can show some of the resulting samples, which in quality really are quite impressive in terms that you don't really have many topological defects. So maybe the main insight of this paper is to separate, the take-home message is to separate the high-level hierarchy, high-level structure from the low-level geometry, learning them separately and improving in that way the generative model of shapes. The last idea that people followed, if you don't want to work from volumetric, from binary volumes, which is convenient, of course, but the problem with binary volume is that you lost some of the information about correspondences, point correspondences between different shapes. So if you want to keep this nice aspect and work directly from meshes, then this is one paper where they propose to do that. And of course, what they have to do is to introduce a first step where they are able to retrieve correspondences and to create templates between shapes. So shapes are registered to a template, the templates are automatically learned, and they retain this part-based aspect where they have a hierarchical decomposition of shapes. So all of that is put together really nicely in some probabilistic deformation model. And then in a second step, at the end of that step, what you would have is, let's say, co-registered meshes where you know which point correspond to which on all points in your database. And then you can train directly a generative deep learning model, which tells you a generative model of surface meshes. So to illustrate, here it's an illustration of what they called part-based model, where you have the legs, etc. The deformation model is quite standard. It's reminiscent of expectation maximization iterative closest points. So it's really, I'm going to skip the details, but you have, you define the part templates, you define the input shape coordinates, the labels, so the association between points on meshes and which subpart they belong to. And then they have a joint cost function made of several terms, which altogether form a probabilistic model of deformation. So for instance, phi 1 would be a unary potential which encourages corresponding points in the template and in the shape to be close from each other after deformation. So this is all trained by mean field inference. And the other building block is a generative model of surfaces, which again gives you a way to know the main modes of variability for surface points on your mesh. And you are allowed to have missing parts for different shapes. Let's say some chairs don't have arms, so you are allowed to have missing parts. And they propose a deep Boltzmann machine to, as a generative model of shapes. So the latent layers are quite standard. It's really a deep Boltzmann machine, so Bernoulli variables. And the only difference is here, the outermost layer, which maps the first layer of latent variables to the observed point coordinates, and this one uses a mixture of beta distributions. The reason for that is that if you look at a given point, let's say the foot of the chair, across all the data set, the distribution of the location of this point is really multimodal. And a nice way to represent that is with beta distribution. So it's a compactly supported distribution between 0 and 1. And you can play around with the maximum probability location to be anywhere between 0 and 1. So intuitively, if you take a mixture of such distribution, you can model this type of multimodal behavior depending on whether you're looking at a bench or a chair or other type of objects. Okay. When you put it all together, what you have is a really quite fancy framework in a way, quite interesting, where you have as input a data set, completely unsupervised, and as output you would get fully registered surfaces, a generative model of the surfaces, and segmented surfaces. So for each point on the meshes, you know which semantic part they belong to. And it really requires minimal user supervision here. So it's interesting in that they were working directly from meshes compared to other work. So now to come back to medical datasets, and I'll finish with a few quick ideas around medical datasets and what can be done specifically for these datasets. So it's interesting to look at how much they differ from this computer graphics dataset and how similar they are. So you have maybe this type of differences. Maybe in medical imaging we have less gross variability. We don't have these large topological and geometric changes. But on the other hand, there is really subtle geometric variability, and we really want to capture it accurately. And the issue that comes with that is that now misalignment between shapes has a much more important impact, because what you're interested in is really subtle. So here maybe the focus would be much more, it would be really interesting to have an approach where you can avoid where you can avoid registration altogether. Let's say you could have a generative model which is directly naturally invariant to pose. And there is a natural framework to do that, is to spectral shape analysis. It's been used really widely in the computer vision and medical imaging literature, a lot of applications, shape retrieval, metrics for shape dissimilarity, functional matching. It's also interesting for shape analysis. I'll give a quick intuition and I'll finish on that. So the idea of spectral shape analysis is that if you look at vibrating plates that have different geometries, and the way and the patterns that are created by sand on these vibrating plates, they really depend on the geometry itself. And the frequency at which these patterns are created are also dependent on the geometry. So you can actually use this information, the discrete set of frequencies at which this pattern is created, as a signature of the geometry. And this signature is invariant to pose. So I'll skip all the details, it's not really important. The idea is that you can represent any functional signal as a combination of these patterns that are created at different frequencies, which are eigenmodes of the Laplace-Beltrami operator. And you can do a lot of mesh processing operation with this kind of, within this kind of framework. So for instance, it's been used for shape classification, shape analysis. I'll skip all these details, it was optional anyway. One thing that I'd like to show is, just to give you a quick intuition of the limitation of this kind of framework when they are applied directly. Here, let's say you have a data set of leaf shapes, different species, and you want to, in an unsupervised manner, to find the different species and to find the modes of variability. So here I show two different clusters that have been learned automatically, and you can see that the modes of variability that have been learned are quite sensible. For instance, one would be the length of the stalk, or sometimes it can be how elongated the shape is or how round it is. But what you can see also is that you have outliers that have been poorly clustered, because here there are dents in this shape and they have been missed by the algorithm. And the reason is that it's really a fine detail, and this type of approach doesn't allow you to capture this type of fine detail. So for it to happen, it will need to be, you will need to pursue this type of framework in a hierarchical manner. And this brings us to maybe a perspective work that has been done on GraphCNN, which tries to bridge the gap between this type of methods and the deep learning approaches. And I think it's quite tricky. I haven't seen much work on using this type of GraphCNNs for shape analysis, but it's been applied already on for other applications, such as shape classification, for instance, Alzheimer's disease, cortical surface parcellation, so you label every point on the surface, or learning similarities on connectivity networks. It's not only for shape analysis, it can be also for general graphs. So it's an emerging field which has quite a lot of potential. Concluding words, again, several possible ways to represent shapes, to build these generative models of shapes, either based on volume-based representation or mesh representation. They all come with their own limitations and advantages. There has been quite some work to try to depart from models that just that have no semantic understanding of the shapes, and try to introduce some structure in the learning process. And yeah, the other direction of work is trying to incorporate in this model natural shape invariances, such as invariant to pose, and so on. And thank you. Thank you first.